Thank you, Alejandro. Thanks everyone for being here this morning. Thanks to the organizers for inviting me to talk about white dwarf pulsations. So there are a lot of things I could talk about with white dwarf pulsations. There's a lot of great results over the last few years, but I actually kind of wanted to do a little bit more of an introduction to white dwarf pulsations because I think most of us in the room are not astroseismologists. There are lots of us in the room that are. But I love this movie from Mike Montgomery. This is showing if you could resolve the surface of a pulsating white dwarf, what you'd see. And you'd constantly see temperature variations coming and going at a bunch of different periods. And so we often work in light curves with pulsating white dwarfs. So this is time in seconds. And this is how much brighter the star is getting. So at certain phases, GD358 is getting 15–20% brighter. And it's on a time scale of a few hundred seconds. And pulsations give us this opportunity to see the insides of stars. You've already seen this plot from Noemi Giammichele's paper in 2018, trying to measure the chemical stratification of a dB white dwarf. And this is really the end goal of what we want to do. We want to be able to build models that match our observations to tell us what's going on in the core, what's the carbon to oxygen ratio, what's the helium content, how do these chemical profiles change with depth in the star. And so these are logarithmic mass fractions that you often see through seismology. And what this is really telling you is 99% of the mass is interior to these inner two decks. And so you're talking 10 to the minus 10 by mass of the star all the way out here. So I mean, this is the surface on these plots, that's the core. And the end goal here is to have some unique constraint. And the keyword here is unique structural constraint. And so there have been a number of papers to follow up Noemi's paper talking about how unique this structure is. And so I actually want to avoid talking about some of these unique astroseismic solutions, and I just want to talk about seismology a little bit more generally today. So we think that pulsations are a natural phase for all white dwarfs. And it's driven at the onset of a partial ionization zone or a convection zone, and that partial ionization, basically an opacity change, you can store and release energy. And so that happens at high temperatures for carbon or oxygen. These are the DOVs. There are DBs that pulsate at about 30,000 to 20,000 degrees. But the most numerous white dwarfs that we know that pulsate are hydrogen atmosphere white dwarfs, and those are the DAVs. And so there are some great reviews that I put up here that talk about white dwarf pulsations across the instability strip. But I just want to talk about the pulsating DAs this morning for a little while, because they're the most numerous, and we have a lot of constraints now from Kepler and K2. And so I wrote a pretty long AppJ supplement in 2017 that's going to kind of form the backbone of what I'll talk about today. That was the first 27 pulsating DAs we had seen with Kepler and K2. We have another 50 or so, but they haven't really changed those initial results in 2017. And so the first thing is that most DAs, when they reach the right temperature to develop a convection zone, so that's the blue edge of this instability strip, everything blue has been observed by Kepler. All these open circles are known to pulsate from the ground, and these have all been constrained spectroscopically with their temperatures and surface gravities. And so most white dwarfs, when they get to the right temperature, pulsate to a few percent or a few tenths of a percent. There are a couple of little X's that are pretty deep in the instability strip. So there are some that aren't observed to vary. We think that may have to do with the fact that they have some moderately sized magnetic fields. But the vast majority of DAs that are passing through, they're cooling through this instability strip, will pulsate. And when they pulsate, there are a spectrum of different modes that white dwarfs can pulsate in. And so I've just stolen a model. When you put your models out in the wild, so 10 years ago, Alejandro put models out in the wild. This is great because then you can, use these models and abuse these models. So I'm going to abuse these models. This is not meant to be representative, but it's just to show you that there are all these little red lines at different periods. We tend to work in the frequency domain. There are all these different modes, all these different periods. I'll use period and frequency pretty interchangeably. Period is just 1 over frequency. But there are all these different periods that the stars can naturally resonate in. So they can resonate at really high frequencies of P modes that we do not observe, but we suspect they probably pulsate in those where we usually observe G modes. So this is where buoyancy is the restoring force. And I don't want to get into some of those equations, but just to say that there are all these modes that white dwarfs can naturally resonate in. And I like to think of white dwarfs a bit like a piano. So there are black keys on a piano, there are white keys on a piano, there are more L equals 2 than L equals 1 modes on a piano, in a white dwarf. The spectrum is denser. And so I like to think of the L equals 1 modes like the black keys on a piano, and the L equals 2 modes like the white keys on a piano. There are natural modes that the star can resonate in. They're not evenly spaced in frequency, and so you kind of have to stretch it out in your imagination. So bear with me for this very contrived metaphor. But there's a piano in the room, so why don't we use it? So these G modes are evenly spaced in period. But when you get to the shortest period modes, that even spacing is a little bit destroyed. So I've already thrown at you L equals 1, L equals 2. You might hear this sometimes. What does that really mean? What are the two things that are the most important that set these mode periods? There are two fundamental properties. There are the number of radial nodes from the surface to the core in the star. That's n. And so the highest frequency modes have the smallest n. And then there are also a number of surface nodes. This is the surface geometry. That's what the L is. And so when you hear someone say L equals 1, that means there's one hot-cool transition on the surface. And if it's L equals 2, that means there's 2. All right? In fact, it's a better way to visualize this. Keaton Bell has some great animations that you can explore on GitHub to actually animate spherical harmonics, so you can imagine the period of the mode is how the star is responding here. We do not see radial pulsations in white dwarfs. These are all non-radial pulsations, so they're sloshing modes at the surface. So this is what some actual data looks like from Kepler. And you'll see that there are, we're running here in frequency. We're using units of microhertz, so thousands of microhertz, but really that corresponds to periods of hundreds of seconds. Those are the typical pulsation periods for white dwarfs. And again, what really rules what periods we're seeing are the number of radial nodes from that mode, from the surface to the core, and the number of surface nodes, the L value. If the star is rotating, which most things in space do, you actually break some symmetry and you can get another set of modes. These are the azimuthal order, the M values that you'll hear about sometimes. And so let me animate this from Keaton's lovely animations again, just to show you, you've got modes going with rotation and against rotation, and that gives you these splittings. And so rotation will cause a splitting of modes. That actually allows us to measure the rotation rate of the star for free, which is great. But to do seismology, you need to know what is the radial order of the mode, what is the spherical degree, what's the geometry at the surface, how many nodes do you have at the surface, that's setting the period, and then what's the radial order of those modes. And when you see splittings like this that are nice and clean, that helps you identify the modes. All right, so those are the three quantum numbers that are really important. We're using spherical harmonics for all these things. Okay, so the first thing I want to mention is that there's this dense spectrum of modes that is, most white dwarfs are pretty similar. Most white dwarfs have a spectrum of modes that looks relatively similar to this. But there are lots of modes that are not actually excited to observable amplitudes. We only see a handful of modes usually. For a star like the Sun, you see all of the modes in a frequency range when they're excited. Stochastically driven pulsators give you a lot of information. The white dwarfs are very stingy with the information they give you when they pulsate. You only get a handful of modes. And what really sets that has to do with how the star is cooling through the instability strip. And so I'm going to give you a map, and I'm going to keep going through this map for the last half of this talk, just to talk about a couple of different things that happen along the evolution of a DA white dwarf as it's pulsating through the instability strip. So the big takeaway here is that there's a convection zone that develops right on the blue edge of this instability strip that's very thin. And that convection zone deepens as the white dwarf cools. As that convection zone deepens, the thermal timescale at the base of the convection zone lengthens. And that's essentially what's setting the periods that are getting excited. We don't get all of the modes excited. There's some selection effects that happen. But here is, in red, is something that's at the hottest edge of the instability strip. And so this is what the pulsation spectra look like. And then as you cool, you get a little higher amplitudes. The periods get a little longer. the frequencies get a little lower. You get in the middle of the instability strip, you get lots of pulsation periods. Amplitudes are pretty high, periods are getting longer. And then all the way at the edge of the instability strip, these periods start to get really long, beyond 1,000 seconds. And so let's take a few steps through the instability strip, because there's some fun things that we can learn just from the space-based observations we've been collecting. And so the first argument I want to make is that we observe the very shortest period, the lowest radial order modes in the hottest white dwarfs. So we observe the very shortest period modes, and those tend to give us the most information. They're kind of the best. And so when we find pulsating white dwarfs that look like this is one white dwarf that was observed by Kepler in K2. Again, we're working in frequency space, so this is frequency, but I'm showing the periods on the top right of these three different modes. And because the star is rotating, you can identify these modes very accurately. They're all split by the same amount, roughly. They all live at similar depths in the star. The star is rotating at a similar rate where these modes live. And from these rotational splittings, we can actually identify the modes. And let's just focus on the simplest L=1 dipole modes that we see in pulsating white dwarfs. So from the piano analogy, there is the highest frequency black key that I can excite this piano at. That is like the first radial overtone mode. And if you look at the periods of all of those modes, that's what's here in the bottom left, that's what all of those that is what L=1, N=1 modes live at a similar period. You could do the same for the N=2 modes, the N=3 modes, N=4 modes. They get a little deeper. The periods get a little longer. But they all cluster together in mode period in an interesting way. And I have to bring out some models to explain why that's interesting. This is what we observe. These are the L=1, K=1, N=1, N=2, N=3, N=4 modes, the first four radial order modes. And if we take these same models that Alejandra has put online that have a range of hydrogen layer masses, and we just randomly pull the N=1, 2, 3, and 4 modes from those models, they can almost be at any period that we see between 100 and 350 seconds. But if we only pull modes from the models that have canonically thick hydrogen layer masses, they start to clump together in groupings. And so without doing any seismology, just by looking at the models, looking how the modes cluster together, we start to see patterns. And this is following some work that Chris Clements presented at a European White Dwarf workshop all the way back in 2016. This has been around for a little while, but the idea here is that there are lots of structural similarities in these white dwarfs. Otherwise, we wouldn't get these mode clumpings. So I think that's a really fascinating result that's come out of the first Kepler data, just because you can immediately identify the modes. Okay, so that's at the hot end of the instability strip, where we have short period modes. These short period modes actually tend to be very stable. And so you can measure rotation rates most of the time when you have relatively warm pulsating white dwarfs. And so I'm going to leave this slide up for a second. We were able to measure rotation in dozens of these pulsating white dwarfs. And we're also able to measure their masses from spectroscopy. And so these pulsating white dwarfs give us good insight into what is the typical rotation rate of an isolated white dwarf. So this is the white dwarf mass on this axis. This plot is from a paper from Jim and others talking about the internal angular momentum loss of stars as they evolve. And so these red lines here are basically model predictions of white dwarf rotation periods as a function of mass. If we break these white dwarf masses up into different mass bins, and we go to the highest mass white dwarfs that come from the most massive stars, there is some slight evidence that they rotate a little faster, on the order of a few hours, compared to roughly half a day to 2 days. But if you take your average 0.6 or 0.7 solar mass white dwarf, they tend to rotate between about 1 day and 2 days. So that's a very typical rotation rate for these white dwarfs that we get for free from these rotational splittings from seismology. So I'm only showing you the L=1 dipole modes, but stars, many white dwarfs have L=1 and L=2 modes, and the rotation that you infer from the splittings is almost always the same. So we're pretty confident that these are good rotation rates. So that's another really nice thing that's come out. I won't spend a lot of time on this, but Mike Montgomery had a great paper in 2020 exploring the fact that as these white dwarfs cool, at some point, at about 800 seconds, so these are pulsation periods at about 800 seconds, those modes actually reach the base of the convection zone. And I showed you the movie at the beginning of this talk. The convection zone is responding to these pulsations. And so the outer turning point for those modes are touching the base of the convection zone that's constantly changing. And so they start to lose phase coherence. And so the shorter period modes, if you look for many months with Kepler data, they have these very, very sharp features in Fourier space. But the longer period modes, this is now in the same exact star, but this is a 922-second mode in that same star. It's almost looks like it's stochastically driven. And that's because the mode isn't stochastically driven, it just loses phase coherence most likely, responding to the changes at the base of the convection zone. So there's a lot of interesting physics you can learn about convection from modeling where this transition happens, but for most of these pulsating white dwarfs, it happens at about 800 seconds, kind of like in the middle of the instability strip. I want to finish with one of the most interesting discoveries in the last 5 or 6 years with these pulsating white dwarfs, and it's that the pulsations can actually resonate with themselves. And the consequence of that is shown here. We've been calling these outbursts, so don't confuse them with CV outbursts. This is all happening in the white dwarf, in an isolated white dwarf. And so here on the top panel is 70 days of K2 data, and all in green are what we're calling these outburst events. And a zoom in on one of these outburst events here is shown on the bottom. So this is just time in a few hours. And the pulsations are marked in red. And then during the outbursts, the pulsations are still there. Their amplitudes are much higher. But the star's getting about 15%, sometimes even 40% brighter during these outburst events. So that 15% flux increase corresponds to almost a 1,000-degree surface effective temperature increase. We're talking about 10 to the 33, 10 to the 34 ergs of energy in these events, but they're completely stochastic. There's no periodicity to their recurrence. They last for a few hours. They very rarely last for longer than a day. Somehow we missed these in the ground. Maybe we had one example of this before Kepler and K2. But with Kepler, we were able to observe 71 pulsating white dwarfs in the DA instability strip to really, really good limits, really, really high signal to noise, and about 20% of them showed these outbursts. And if you only focus on the temperatures in the instability strip, if you go to the coolest pulsating white dwarfs, more than half of them show these outbursts. So it's a feature that's happening as white dwarfs cool. I mean, this is what will happen for our sun, most likely, in 8 billion years or something. It'll go through these pulsations, and then it'll go through these outburst events. And very quickly, to sort of get a handle on what we think is happening, we think there's some rapid transfer of energy from a parametric resonance between a mode that's driven and two modes that aren't driven, that actually break near the surface of the star. And those two modes that aren't driven are stealing energy from the mode that is. And so I'm going to steal some representative model of this object, similar in temperature, similar in mass to spectroscopy. It's not a perfect fit, but just imagine that some of these pulsations that we observe are L=1 modes. A couple of them are L=2 modes, but there's this whole spectrum of modes that the white dwarf can resonate in. But as you go to the longest period modes, those modes can't actually reflect anymore. They actually break at the surface of the star. It's as if half of the piano still had strings, but it didn't have hammers to hit those strings. And so if you tried to excite those modes, they wouldn't resonate. So they're damped rather than driven. And so that half of the piano is off limits, but there's one mode, you know, fairly in the middle of the tune that's driven. I like waking everybody up with the piano. It's a good gimmick. This mode right here is at a frequency that if you have two modes that are not driven, but you add them together, their frequencies together, they equal this mode that is driven very, very closely. So there's only about a 1/10 of a microhertz difference. This is just a model, but there are lots of different modes that you could imagine coupling here. But this L equals 2 mode and this L equals 1 mode could add together to get you this parent mode. And so it's very likely that those daughter modes are leaching energy from that parent mode. That energy is rapidly dumped in the convection zone, heats up the surface of the star, and gives us these outbursts. So this was something that Yanqing Wu and Peter Goldreich pretty much predicted 20 years ago for Yanqing's thesis. Xing Wan has done some great follow-up work a few years ago with Peter to really confirm that that's very likely what's happening, that these parametric resonances are stealing energy. And so these white dwarfs are going into some limit cycle and dumping energy at the surface of the star. And eventually, at the edge of the instability strip, white dwarf pulsations die off altogether. We would expect white dwarfs to pulsate all the way down to several thousand degrees. Driving probably works there. But for some reason, we don't observe pulsations below about 10,500 degrees. And it's very likely to do with some combination of this mode coupling and actually taking energy away from objects at the red edge of the instability strip. So that's sort of a conclusion of our quick tour through the instability strip. So just to summarize, these really short period modes can give us a handle on how similar white dwarfs are. I would argue that, some large fraction of white dwarfs have very similar hydrogen layer masses based on the clustering of their periods that we see. The stable modes can give us their rotation rates. Most white dwarfs rotate between about 1 to 2 days. They're pretty boring. Fast ones are more exciting, like you heard about yesterday. The longer period modes start to feel the base of the convection zone, so they're harder to get constraints for seismology on because you can't measure their periods as accurately because they're modeled up. But this mode coupling is probably giving us outbursts. And so I think that's a good place to stop. Love being here. Thanks for all your attention, and I'll take some questions. Thanks.
Hey JJ, great talk. Like in the top diagram in the instability strip, there's a kind of trend for things moving towards lower gravity among the blue dots. Is that a kind of bias in the target sample, or?
Could you say that one bit more time? What's the trend you see?
If you look at your cloud of blue points, as you go to lower temperatures, they drift towards lower gravities. And is that a selection effect in the bias in the sample that Kepler observed, or? I mean, it's quite clear, and it's actually going in the opposite direction of the spectroscopic fits, which were rising towards higher gravities at lower temperatures, which is an artifact in itself. But
yeah, so I will say that all of these temperatures have been corrected for the 3D corrections. The selection function for these pulsating white dwarfs for Kepler and K2 was completely random because we didn't have Gaia, and so it was basically things with modest proper motions. So I can't imagine a big selection bias towards less massive things, but it's an interesting question. So I don't know if it's overcorrection from the 3D or what. Because the 3D corrections start to really, really ramp up at these temperatures at the red edge of the instability strip. Like tenths of a deck, I think, right? So.
Yeah.
Next question.
Hi, JJ. It's nice detailed talk. I have 2 questions for you. When we go towards this lower end of temperature, I mean the right side of the instability strip, how deep we develop the convection zone? Is there any idea?
How deep will we develop the convection zone? I mean, I think, I mean, as things cool through the instability strip, it just keeps getting deeper. So I think really the constraints that we have are that we know that there's some connection between the thermal timescale at the base of the convection zone and the periods we observe, and we tend not to observe a period beyond 2,000 seconds. So whatever that depth ends up being, that's where they stop being driven, but that doesn't necessarily mean that those modes, there are certainly modes being driven with deeper convection zones at cooler temperatures. We just don't observe them to pulsate.
Okay, and it's nice to have a such type of tone when we go from the higher end to lower end while cooling. So do we have a different kind of tone for lower mass to higher mass white dwarfs while cooling?
A different kind of what? Sorry.
like different kind of notes, L and N.
Oh, yes. Yeah, so
they will make a different music there.
Exactly, yeah. So as you go cooler, you start to see more and more periods get excited. There's sort of always a mix between L equals 1 and L equals 2 modes as the white dwarfs cool. We haven't seen a major trend. It's really hard to identify these long period modes, though. And so it could be that they are preferentially L equals 2 modes or some different kind of overtone, but it's a bit hard to identify them because they all start to overlap, because we identify them from even spacing and frequency, but even spacing and frequency down here starts to overlap with everything. So it gets a bit tough for the long period modes.
Nicola?
Hi, JJ. So you said that we see clustering around the canonical 10 to the minus 4
Hydrogen.
Yeah.
Hydrogen thickness. Thank you. So from astroseismology, what is, do you have a sense for what is the thinnest hydrogen mass that has been reliably measured with astroseismology?
Yeah, I mean, there are certainly, you know, I think this grid goes down to 10 to the minus 10. Barbara, you have grids that go down basically the same hydrogen layer mass, I think. And, you know, you can fit the observed pulsations well with very thin layers. But the question is, how unique are those fits? And yeah, maybe Barbara can speak to cases where it is very clear that there's a very thin hydrogen layer mass.
Actually, I can answer that because I computed those things. We think that it's around 10 to the minus 10 because at those temperatures, convection will mix the hydrogen to the helium if it's thinner. So it's actually more a convection limit than the pulsation limit.
I just wanted to add a comment.
Okay.
Oh, JJ, thank you for a fantastic talk. I'm curious, I'm not an expert in the field, but I'm curious, you said when you presented the effective temperature log G diagram, in this instability strip, you presented crosses as white dwarfs that are maybe magnetic. Mm-hmm. So I'm curious about the effect of the magnetic field in the quenching of pulsations. Can you comment on that?
There are certainly other experts in the room who are better suited to answer that, but I think the idea is that you just need tens of kilogauss field to inhibit convection.
Yeah, that was my next question.
These convection zones are so thin that, you don't need much of a field. So I think, you know, I hope at some point we start chasing up. We have really good limits on some of these that they don't pulsate to hundreds of parts per million in some cases. Okay. And so they're definitely not variable. So it'd be great to do spectropolarimetry or look for really fields.
Just one thing, Barbara,
thank you.
Short comment.
Yeah, no, from the observer perspective, following the theoreticians in terms of the thickness of the thinness that we could go, we use 10 to the negative 10 solar masses for hydrogen. And the grids that we calculated, we have never found the need to go even thinner than that. So we never seen anything that would indicate that it would be lower than that amount.
Yeah, you kind of lose sensibility after that. Paula.
So just a comment about the magnetic field. V455 and is an IP, so its field is probably 1 to 10 megagauss, and it has pulsations. So they do exist. The question is, like, why?
Yeah, there's one very frustrating white dwarf that is a DB PG0112, and it has beautiful pulsation spectra, and it shows a spot at 10.1 hours. If it had a 10 kilogauss field, we'd see its effect on the pulsations. So there's a weird, yeah.
McCormick?
Yeah. So the outbursting ones, why do you see only half of these cool ones to show outbursts? Why is it not all of them? Because the model that you presented, you know, would indicate that they should all show that.
Yeah. So there are certainly cases where they're outbursting and we're not catching it. So I tried to cut out some slides for time, But this is an object that we looked at the very beginning of K2 for 9 days, and it didn't show outbursts. And it didn't show outbursts for more than 60 days, and then it went into this wicked 40% outburst. And so it's likely that this nonlinear resonance effect needs the modes to hit some limit cycle, and that doesn't happen all the time. And so probably most of these things that are the 50% that aren't actually observed outbursts, you know, some large fraction of them probably are outbursting, we're just not seeing them. So the recharge timescales are so long that we've just missed them. Yeah.
Okay, and one, oh, Mark, oh, sorry.
Just to Paula's point about the intermediate polar, I just wondered if the kappa mechanism could be driving there, and maybe it's not convective driving.
Okay, last question here.
Thanks a lot for this really nice talk. I have a quite more like an open-ended question. So like this works really nice for like isolated white dwarfs, right? So to which degree can you apply the same things on white dwarf binaries, and can you learn anything about their composition and so on?
Yeah, no, this is a great question about, I mean, yeah, what can you learn about this? I mean, I think this is Jim's wheelhouse, and you know, dynamical tides and close white dwarf binaries, and so you know, I'll defer to him to have that conversation with. But yeah, I mean, there's certainly lots of information we can hopefully glean from these really close binaries. With you know, they're in that case the tides are raising quadrupole L equals 2 modes, so the spectrum is basically the same as for these pulsations. So yeah, you're very similar physics. Yeah.
So we thank JJ again, and we move to our next speaker.